Let's talk about velocity time graphs, the VT graphs. So, how does their shape help us determine the type of motion, and what kind of information, quantitative information, can we find on a velocity time graph? So, I drew some examples here, and I'm going to try to briefly see if we remember what we've done in grade 11. So, the first graph on the top. So, let's actually label them. This is A, B, C, D, E, F, and G and H. So A represent, and I'm sure that you already know, a uniform motion. So anytime, and so does B, uniform motion. So anytime you see a velocity time graph that is a horizontal line, it means that the magnitude and direction of velocity is not changing. However, in A, we're moving on the positive direction. In B, the object is moving on the negative direction. C represents an object at rest. The velocity graph happens to land on the time axis. Now, anytime that the slope of the velocity time graph changes, it means that the value of the velocity is changing. And if you see a straight line, it means it is changing uniformly, so which means the acceleration is constant. So all of them represent the uniform accelerated motion, the rest of the graphs. However, the first, so I'm going to write here uniform accelerated motion. However, this one is moving on the positive direction. But not only that, we have to determine what is happening with the object, with the velocity. Well, in this case, is speeding up. Sorry, speeding up, right? The second one, it's uniform accelerated motion. It's still moving in the positive direction. Remember, a velocity time graph going downward, but it's still above the time max. It means the values of the velocity and direction are all positive, just that the magnitude is decreasing continuously until it becomes zero. So in this case, is a uniform accelerated motion moving in a positive direction, but slowing down, right? The next one, graph F, is again uniform accelerated motion. However, it's moving in a negative direction. All right, the acceleration is positive, but the direction of the motion is negative, which means that our object is still slowing down. All right, make sure that you understand that that's usually where we have our misunderstanding or misconcept with regard to graphs. These velocity time graphs are the one that confuses us the most, and we'll have these graphs on a test and on the exam. Right, velocity time graphs are my favorite graphs. The next one represents again a uniform accelerated motion. It's moving in a negative direction, but pretty obvious is speeding up. Right, the value, the magnitude of velocity as you go down, so it goes from 0 to -1 to -2 to -3 to -4. So its magnitude is increasing. Remember the sign, those minuses in physics represent direction. So it's just speeding up on the negative direction. All right. For graph F, the same idea, right? It goes from -5 to 0, but still in the negative direction. And the last one is a uniform accelerated motion, but it's moving in a positive direction, is at rest for a while, and then it moves in a negative direction, right? In this case, we have to divide the motion into parts, right? So we have two parts. Part one is moving in a positive direction, but it's slowing down. Then here, point where anytime the velocity time axis the velocity graph crosses the time axis, it means that the object is at rest for that moment, okay? The part two is moving in the negative direction, but now is speeding up, all right? So those are the general shapes of velocity time graphs. How do we get information now? Quantitative information, right? So let's write here quantitative information. We cannot get initial position. Velocity time graph does not tell us that. We have to make assumptions. We cannot get final position, all right? But we can get displacement, and if you recall this from grade 11, or if you did the reading of chapter 1, it's the area under VT graph. Remember, above time axis is positive, and below time axis is a negative direction. Can we find the distance traveled? Yes. We still use the area under VT, but now since it's scalar, everything is positive. We'll just add everything. We're going to do an example later on. Can we find average velocity? Yes. Once we find the displacement, we recall that average velocity is delta D over delta T. Since we can find both of them on the graph, we can find average velocity. Can we find initial velocity? Absolutely. All we have to do is read the graph. All right. Can we find final velocity? Yes, we can. All we have to do is read the graph. And lastly, can we find the acceleration? Yes, we can. And all we have to do is find the slope of the graph. All right. Sorry, I forgot to add delta t. Yes, we can. All we have to do is read the graph. All right. So that's the velocity time graph. Sometimes we have to pair or match, rather, graphs, right? So for example, if I do a graph like this, that is a position time graph, right? And I give you a few options of velocity time graph. Here's option A. Here is option B. And here's option C. And I would say which velocity time graph corresponds to our position time graph. So this is given, we want to find. And if you look at them, you want to see which one corresponds to our position time graph. Well, the first of all, this is a uniform accelerated motion. So the best thing to do is describe this one, and then it helps you figure out which one matches. Okay, so it's uniform accelerated motion. Is moving on the positive direction and is slowing down. So now I look at my velocity time graphs. The first one represents a uniform motion, right? So this is not good. Now the choice is between B and C. They both represent uniform accelerated motion, and they both are above the time axis, which means it's a positive motion. However, the first one, the velocity is increasing on B. On C, is the only one velocity is decreasing. So the answer would have been C. All right. These are a good way to practice with. Again, on that PowerPoint conceptual quiz that is on B12, you have questions like this. So I strongly encourage you to complete that one. All right. And the next one now is acceleration time graph, which is going to be very short. And then we're going to do an example of velocity time graph with numbers.